to just change our focus a little bit here from talking about what a y value is. We've been trying to estimate particular y values. We're going to change our focus to how much the y value changes as I change my x value. And as we do that, we will define these things called differentials. All right, so I've got a picture up here. We've got y equals f of x is this lovely curve. Y equals L of x is the tangent line, or the local linear approximation of that curve at this point x naught. Okay, and so far we've been focusing on, well, what happens if you pick a nearby point and you wanted to calculate the value of the function there. So here, if I wanted to know that y value for this nearby point, we've been saying that might be difficult to calculate, but the y value on the line for that same x value is easy to calculate. So we've been saying the y value here is a good approximation of the y value here. Okay. But if these points are close, I can describe here, I'm just going to say that's delta x. That's the amount that I've changed my x. Now that's going to be a signed quantity. Here I've drawn it with delta x being positive because my second point was to the right of the point of tangency. If my second point was to the left of the point of tangency, delta x would be negative. Okay, and now on the graph of f, I can mark off. Here's delta x, that's the horizontal change between those points, and this would be delta y, that's the vertical change between those points. And to calculate that vertical change, I would simply have to calculate both y values and then subtract. So delta y is just f of x plus delta x, because that would be, x naught plus delta x. That would be the x value that I have here, minus f of x naught. So it's just the difference in those y values. Okay, now I can do something similar on the tangent line. The point of tangency is on both the curve and the line. And this point here, which has the same second x value, x naught plus delta x, just has a different y value. But I could mark off the horizontal change and the vertical change on the linear function. Okay. Now, I've already used the symbols delta x and delta y, so I don't want to use the same symbols here. So what I'm going to use instead is dx and dy. These are my new symbols, and these are what we call differentials. Okay. So we've seen them before in the context of the ratio dy by dx, which is just the derivative. Now we're going to talk about what they mean in their own right. Okay. So I'm basically thinking of dx as being a horizontal change between 2 points on the tangent line, and dy as being the vertical change between 2 points on the tangent line. Well, I've got words for that. I can say dx is the run of the tangent line, and dy is the rise of the tangent line. But I need to be careful here, because if I have a line, it doesn't have a set rise and a run. It has a set ratio between the two of those. If I went to talk about a point here, I'd have a bigger run and I'd have a bigger rise. So I'm not thinking of these as fixed values. I'm actually thinking of these as variables. So I have two new variables that have a relationship between each other. So I'm going to think of dx as my independent variable, independent variable. Independent variable means it's the one I control. It's the input. I can choose what I'm going to make it. And you can see from the picture here, I've chosen to make it the same as my delta x for this particular picture. Okay. dy, what's representing the rise of the tangent line, is simply going to be the dependent variable. That's the output variable. So that's saying if I know what the run is, I can calculate the rise. Okay. So if I know how much I've changed x, I can calculate how much that's going to change y on the tangent line. Okay. That's kind of neat, because on the graph of f, knowing that I've changed x tells me I've come to a different point, but to calculate the change in y, I actually have to calculate both y values and then just subtract. On the line, I'm going to be able to do that much more efficiently, because I have this fabulous relationship. Rise is equal to slope times run. So I can say dy is just going to be the slope of my tangent line at the point of tangency times dx. So if I know the slope of this line and you tell me the run, all I have to do is multiply the run by the slope and I know the rise. Okay. Now, how is this going to be useful for us? Okay. Well, the basic idea is this. If we set dx to be delta x, so if we make the horizontal change between points the same for our linear function and for the function that curves, for f of x, then delta y can be approximated by dy. So if I want to say, okay, I'm going to change my input a little bit, I want to know what the consequences are. I want to know how much is that going to change the output of my function. If that's a difficult calculation, this one should be an easy calculation. I can say I can approximate the change in the actual function with the amount of change in the original function. Okay. And I can do this at any point. So I've labeled this here as the point of tangency was x naught. In general, I could change this. I could move to a different point x. Then I'd obviously have a different line and therefore a different slope. But we define dy as the differential of a function f of x. We define that to just be f prime of x dx. Now when we're using it, we'll always be plugging in a specific number for x, and we need to have a specific number to plug in for dx as well. Okay. But this is my formula for the differential. So if I wanted to use a differential over here, I'd calculate the derivative here, I'd determine how much I wanted to allow x to change, and then I could use that to approximate how much y is going to change. Okay. So this is the formula for the differential. I want to just emphasize that when we use this, we actually have two variables that we need to plug in for. So when we use the differential, we have to plug in for both x to indicate which tangent line are we working with, which slope do we want, and dx to say what's the run. If I know which line I'm working on and what the run is, I can calculate the rise, and I can use that to approximate the amount that the actual function will change. We've been going for a little while here, so I'm going to leave this video as just sort of the definitions of things. I promise in the next video we're going to do an example of calculating and using a differential.